Hi, my name is Hanspeter Pfsiter, and I would like to thank the organizers of VDS for inviting me to give this keynote. It's a great pleasure to talk about our work in visually interactive neural probabilistic models. We live in the golden age of deep neural networks, which are machine learning models that consist of functional units, each with tunable parameters, assembled into a compute graph. These deep neural networks are capable of tremendous performance in various applications, especially in computer vision, including image captioning, live video captioning, in robotics, or for self-driving cars, but also in natural language processing, for language translation, conversational bots, or tasks like language modeling. However, we might ask the question, do we completely understand how deep neural networks achieve these amazing results? And spoiler alert, the answer is no. In general, bigger neural network models with millions or these days billions of parameters yield better performance. And they are difficult to understand and debug. So it's really more of an art compared to a science. As Twitter users Hard Maru says, AI research is sometimes more like an art than a science, or like alchemy, as they say. Now, I would like to compare this to this picture of 3 Mile Island, which is a nuclear reactor in the US that had a partial meltdown in 1979. During the crisis of the meltdown, apparently there were 600 signals and alarms going off in this control room, and the poor operators had to make sense of what is going on under very critical and very life-threatening situation. And we are somewhat in a similar situation, maybe not as life-threatening as a nuclear meltdown, but certainly in terms of numbers of parameters, it's just impossible for humans to really understand what deep neural networks are actually doing. I would like to bring us more in line with what is known as human-centered design, where technology has to be designed in such a way that humans can use it, even when we are stressed out or tired or just liable to make mistakes. The interfaces around us need to be accepting of human limitations. They have to present a world comprehensible to us, and that's the idea of empathy. Ben Schneiderman calls this human-centered AI, and he says that AI needs to amplify, augment, empower, and enhance people. And we need to have insurance for human control while increasing automation. And the good news is that we can have both. We can have high levels of human control and high levels of computer automation at the same time. We would like to call this human-AI collaboration, where a human team, Caesar, Anna, and Bert in this picture, are collaborating with an AI, in this case Irene, our friendly robot here. Now, in our work, the team of humans consists of researchers in machine learning, such as Professor Sasha Rush at Cornell University, and researchers in visualization and HCI, such as Hendrik Strobel at IBM Research. We also have several of the postdocs in my group as part of this team. And what I'd like to do is I'd like to talk to you about our journey in making visual interfaces for deep learning models in natural language processing over the last several years. And I'm going to start with our work in LSTM-Viz, which was all about observing the parameters of this very complicated deep neural network that is used for language processing. At this point, we were mostly concerned with trying to understand what's going on inside the model, so there is no interactive control in this particular project. In Act 2, I'll be talking about interacting with our model through a visual interface. And I'm going to use the example of Seek2Seek-Viz, which was a follow-up project onto LSTM-Viz. Again, another language model that, in this case, we not only could observe, but we could also interact with by changing some of the decisions that the model made, in this case, during language translation. And then in Act 3, finally, I'll be talking about human-AI collaboration, where in 2 projects, CSI and Jenny, we basically built hooks into our model that allow us to control the model in a way that is human understandable and that allows us then to change the output to influence how the model works. And I will of course talk in more detail about each of these 3 different approaches to human-AI collaboration. I have 3 fundamental messages. First of all, interfaces to deep learning systems need to follow the principles of human-centered design that I mentioned before. Secondly, to re-establish the human agency over deep learning systems, we introduced this concept of interactive collaboration. And lastly, neural network models need to be extended to include intermediate representations that we call hooks that can be understood and acted upon by humans. So let's get started with Act 1, observing deep learning models. And as I mentioned, we're going to use the example of LSTM-Viz, which was published in 2017. We're looking at RNNs, recurrent neural networks, and a particular type of RNN called an LSTM, a long-time short-term memory network. And RNNs have shown to perform really well in many different language tasks, such as machine translation, image captioning, text classification, music generation, and speech recognition, among others. So let's look first more at an abstract level how they work. Like in many language models that use deep learning, we're starting with our words. In this case, these are words over time, so at time t, t-1, t-2, etc. So this sequence of words is then translated into numerical word vectors. These are the input to the RNN. The RNN converts this sequence of word vectors into hidden states called H. And the hidden states is a function of the current word and of the previous hidden state. So for example, h of t is a function of x of t and of h of t-1. These hidden state vectors are an abstract representation of the whole text corpus over time. And they learn that representation over time, so they have some memory about all of the words that appeared before in this text corpus. And we can use those hidden states then for various language modeling tasks. In our case, we're going to use this to predict the next word that the language model is going to output. So we have an output prediction in the sequence, and in this particular case, that is being used for language modeling. Now, the questions that we started with, that we tried to answer with our project, are why are RNNs so effective at capturing the history of words? And secondly, what does an RNN actually capture in its hidden states? And you kind of have to answer the what question, this one here, before you can answer the previous question, the why question. So we built this visual analysis tool that allows experts, and this is really built for machine learning experts, to formulate hypotheses. What properties do groups of hidden states learn to capture, for example? Then, using the tool, you can refine those hypotheses. For example, what textual similarities do the hidden states represent? And finally, we can compare the models and the data sets to allow early generalization about the insights that these representations provide. So let me give you an example. And we're going to use a very simple language with memory. The alphabet of that language are the numbers 0 to 4 plus 2 parentheses, open and closed parentheses. And what we're going to generate is basically a sequence of open and closed parentheses with randomly inserted numbers. Now the numbers are actually not random in a sense. They're randomly inserted, but they represent the nesting level at that point in the string of open parentheses. So for example, you have open parentheses 1, so that's at level 1 of the nesting of the parentheses, followed by another parentheses and a 2, and that means we're at nesting level 2, etc. Now, we're going to build a visual interface in order to understand what's going on inside the RNN that has been trained on this artificial language. So we're using parallel coordinates for the visualization here, and the parallel coordinates view has on one hand the words on the x-axis. The words here are just the numbers and the parentheses, and those of course evolve over time. So we're starting the sequence, on the left, and then we progress towards the right. On the y-axis we have state values of the hidden states, and those hidden state values again evolve over time. And we can of course look at many different hidden states. So in this particular example we have 650 different hidden states shown here in this parallel coordinate plot. Now, any given line in this parallel coordinate plot gives us the evolution of the hidden state of one particular neuron in this RNN. And we can also define a threshold above which we can say that the neuron fires or is on, and below the threshold the neuron does not fire or it is off. Alright, so let's look at the interactive interface here. So you see this parallel coordinate plot, and we can first of all note that we have, these different nesting levels from the parentheses. So we just overlaid the actual nesting level on the bottom display here. So we might be wondering, there is a certain regularity to everything that's going on here. And you see kind of the regularity of the firing patterns, as it were, of these different neurons. And we might be interested in understanding, is that related to the nesting level? So the user in this case selected nesting level 4 here by just brushing over it. And lo and behold, nesting level 4 corresponds to this particular set of neurons, in this case 2, that fire whenever nesting level 4 is reached. So there are 2 hidden states in this RNN that correspond to the nesting level of 4 in this case. Now we could do similar analyses for other nesting levels, and lo and behold, the firing pattern that we're seeing here is really related to the nesting level of the parentheses that we're using in this artificial language. Now there is more to this tool, but in interest of time I'm going to stop here and just leave you with this impression that this tool is really a visual interface to this complex RNN that makes it relatively easy for experts to understand how these hidden states inside the RNN evolve and compare that to the output. You can actually compare it to multiple outputs and then sort of see the patterns among those different outputs. And if you're interested to learn more, I invite you to play with the live demo at the URL here on this slide. But I want to move on to Act 2 so that we can finally get to human-AI collaboration. And on the way there, we want to look at interacting with these models, because so far we've only been observing them. And the project I'm going to describe here is called Seek-to-Seek-Viz. So Seek-to-Seek models, very similar to RNNs, can learn to transform an arbitrary length input sequence into an arbitrary length output sequence. And they're, again, state-of-the-art for tasks like machine translation, natural language generation, question answering, speech recognition, image captioning, summarization, etc. We're actually going to focus on the specific example of machine translation. So here is the overview of how a seek-to-seek model works. It has 2 separate neural networks. One is called the encoder, that takes again our words, here represented by x1, x2, x3, etc., converts them into these word vectors or word embeddings, and then into these hidden encoder states. So again, the encoder states really represent the sequence of words in context. On the other side, we have a decoder that, for example, decodes those hidden states and then outputs a different language. So this is, again, in the example of machine translation. The decoder very similarly has word embeddings, decoder states, and also a context state that is used to connect the decoder to the encoder. And it emits words that are shown here as Y1, Y2, Y3, etc. In this case, in a different language. Both encoder and decoder are connected through a mechanism called attention. And attention is a weighted average of the encoder states and the current decoder states. And it helps to predict the next word. So it tells the encoder on which words to focus to predict the next state. Attention is actually really interpretable, as you will see in the visualization that I'm going to show you next. Once we have the decoder will make predictions over the vocabulary of output words. And it creates a probability distribution of potential output words using each of the decoder states and the attention-weighted encoder states. Now, we could just make a prediction by picking the most probable word at each time step, but that would globally not be optimal. Instead, machine learning researchers have used this search, which is called a beam search, to basically have a tree of these probability states and find the best sequence of the output words that fulfills multiple of these probabilities. So let's look at an example. Again, this is translation, in this case from German to English. The German input is Die längsten Reisen fangen an, wenn es auf den Straßen dunkel wird, which translates to the longest journeys begin when it gets dark on the streets. However, our model translated it to the longest travel begins when it gets to the streets. So it's missing the crucial word dark, which in the German would be dunkel. And we might want to understand what's going on and where did this mistake happen. So how do we do this? Well, first of all, we can use this interface to examine the model decisions. On the top here on this visualization, we have the input, which corresponds to the encoder. Then we have the output from the decoder in yellow. In this case, that's the translation. Then we have the connection between the two, which is the attention, shown here as a ribbon model or a ribbon visualization. And the wider the ribbon, the more attention the output paid to that particular input word. Then we also show the top K predictions in those probability states that I mentioned. And on the bottom, we show the beam search, which is this tree that looks at all of the probabilities, the top K predictions, and then optimally connects them to find the actual output sequence. All right, so I'm going to show you a sequence of steps to try to figure out what went wrong with our translation in this particular case. So the first thing one might do is to check the encoder. And that's pretty simple in this case because the encoder just represents literally the German input sentence here. Secondly, we might want to check the attention. So if we hover over any of the output words, we actually see how they are connected to the input. And so, for example, we can see that where dark is missing in the translation, there is the word to, but to actually seems to have a strong attention connection to the German word dunkel. So that doesn't seem to be the problem because, you would expect dunkel would be translated into dark at that position. Next, we might want to check the prediction model. So we're going to look at the top K predictions in the output. So again, these seek-to-seek models, they output multiple predictions. And so we can actually check how these predictions correspond to the input. So what we're noticing is, and the bar chart at each word shows the probability of that word being emitted. We're seeing that at this critical point here, to and dark have very similar probabilities. And they are quite different than in other cases. For example, longest and oldest at the second word has a very different probability. Longest is much bigger in terms of the output probability than oldest. But crucially, the word dark actually has a high probability of being output. So that might give us a clue that maybe something went wrong in the beam search. So we can check the beam search using this visualization here on the bottom, and we see all of the decisions that the beam search made as it was going through the top k output probabilities. And indeed, we see that the word dark is not, selected here, even though it does have a very high output probability. So this is a debugging cycle that ultimately shows us that there is a problem in the beam search that led to this missing word dark in the output. Now, interestingly, and I think crucially, we can actually check that with some what-if testing. And that's where the interaction comes in. That's how this model is different from just observing. So, for example, in this case, again, we can look at the word dark and we can click on it in the top k predictions, and it will then be selected in the beam tree search on the bottom. And as you can see now, the bottom actually outputs the correct translation, which is the longest travel begins when it gets dark in the streets. So I think what's important to realize is that this interaction here actually changed the output of the model. So there is not just a visual observation, there is also an interaction with the model. However, admittedly, it is somewhat superficial, right? All we're doing actually is changing the output of the beam tree search, which is kind of the last step of the model. Now again, Seek2Seek is online and you can play with the demo. It has many other visualizations that I don't have time to talk about. Suffice it to say that the top views are relatively simple. That's what I showed you so far. And there is more sort of in-depth views for experts on the bottom, where you can actually look at the clustering of the hidden states and how they're connected as the output sequence evolves. But let me get to Act 3, which is really the main event and really what I want to talk about in this presentation, which is collaborating. So as I mentioned before, we're proposing to augment the machine learning models with what we call model hooks. And the model hooks have two purposes. On one hand, on the forward path, they allow us to make predictions about what the model might actually do next. But there's also a backwards path, which means we can actually examine and correct model decisions interactively after they have been made. So to make this a little more clear, let me use this very simple example of a self-driving train. And so you see the scenario here. The self-driving train comes up at this switch here, and it can either go left or right. So as shown on the left, the observation interface here, if we had nothing else, if we did not have the hooks, can tell us where the train may end up, but we don't really know how it got there, right? We know it's going to end up on the top, but it take the left or the right switch. We don't know. On the other hand, on the right side here, once the train reaches the end of the track, we will not be able to see where the train came from. And again, did it come from the left or from the right? So what we're proposing is to introduce these hooks, and we can visualize it here in the form of a switch or of a lever. And so the human actually sets this lever. And so the model, in this case the self-driving train, in the forward path has to take the right path here to get to the top. And similarly, once we're observing that in the output the train is on the top, we can look at the lever to infer that it actually took the right path here. So a traditional prediction model, just as I showed you in LSTM-Viz, has these internal hidden states. So it converts the input words into word vectors into the hidden states. The hooks that we're going to introduce are actually latent variables that interact both with the input, here the xt, and with the hidden states, here the ht-1, to then influence the current hidden state. And by introducing these latent variables, we're able to influence the model decisions in the way that I just described. So to make this more concrete, I'm going to present to you two more recent projects. This one here from 2019 that we call CSI, Collaborative Semantic Inference. And in this case, we use the task of summarization. So this text here on the left, we want to summarize into this shorter summary shown here on the right. But we want to do this in an iterative manner with a user in the loop in a collaboration between AI and human. And the particular questions we're interested in are: what input text generated a particular output? We might be able or want to select different input text and generate a new output. Or, interestingly, we could also change the output and see where it appears in the input. And that's this kind of backward inference that I talked about before. So let's look at the interface here. The interface is relatively simple. It shows you on the left the input and on the right the generated summary. And so the user starts by telling the model, please generate 3-sentence summary from all of the input on the left. So the user can do this by just putting the number 3 there in the interface and then start the machine learning model, and it will take all of the input on the left into account to generate the output that you're seeing here on the right. Now this text here happens to be about water on Mars, and so on the output we see primitive water reservoirs there could have evolved over billions of years, scientists say. Early oceans on the red planet might have held more water than Earth's Arctic Ocean, and scientists used the world's 3 major infrared telescopes to measure traces of water in the planet's atmosphere over a range of areas and seasons. So as you can see, the last output sentence here is selected in yellow, and you can see the attention here. This is a seek-to-seek model where the attention shown here as this yellow ribbon connects this particular output sentence to the input sentence that most influenced it. And if you look on the left, you see the actual input that generated this output sentence. And everything that's underlined in red has actually been used in the particular summary output here. So again, scientists used the words 3 major infrared telescopes to measure traces of water in the planet's atmosphere over a range of areas and seasons. That's what's underlined here in red. So that already helps in understanding how this particular output was generated by the AI model. Now let's suppose the user wants to add a new sentence that starts with "the water is." So what the user can do is enter this sentence by typing "the water is" followed by 3 dots, and that will cause the model to then generate the most likely output. So in this case, the water is very likely wet for a longer period of time than was previously thought, the scientists say. So again, this is a collaborative aspect here, right? So the user actually prompted the model to complete this particular output sentence. And again, in the interface, we can see how this output sentence was generated based on the ribbon connection, the attention connection to the input, and based on the underlined words in the input. Now, we might add another sentence. The user in this case has actually written a whole sentence and did not ask the model to complete it. And the question might be, what does the summary cover now in terms of the input text? And again, we can easily see this by looking at the text that is underlined in red, and it's also shown with this kind of abstract visualization of these outlined boxes here in red, and also the red lines going down on the input text on the left. So what lessons did we learn in this particular case? The users can have a semantically meaningful interaction with the model, because you as a user start to understand what words and what phrases did the summary actually contain from the input text. You can then augment the summary and either have the model complete it or write your own sentence and then figure out, what part of the input is used in that particular sentence. So again, this is what we call human-AI collaboration, or in this case, collaborative semantic inference, because the model is inferring text and the human is also inferring something about the model and about the text. However, another lesson we learned is that it's easy for users to over-constrain this text generation. So state-of-the-art models, even the best models, cannot handle this quite yet. So we left a little bit too much of a degree of freedom for the user to just type in any type of text or to add as many constraints as they liked. So we need a higher level interface to specify these constraints. And so in our next project, which was inspired by this one, we used a constraint graph to specify these model hooks. And this work here hasn't even been published yet. It's going to appear in the IEEE Visualization Conference this year. And the system is called Jenny. In this case, we're using the task of Table2Text Generation. So we have a table, in this case about restaurants and similar establishments. So you can see, name, eat type, food, price range, area, family friendly, near, etc. From which we want to generate output sentences. So for example, the mill is an English pub, or Strada is a pub, etc. Now, in order to do this, as I mentioned before, we want to introduce these higher order model hooks. We don't want to just have the user be able to freeform any kind of output and then force the model to see how that matches to the input. That would actually be too hard, and state-of-the-art models couldn't do that. Instead, we're going to introduce control states, also known as model hooks, and a graph between those control states. You can think of it as constraints, and then those constraints are going to be represented internally in the model as latent variables. And from those constraints, we can then generate output text. And again, we have this interaction here, this collaboration between the model and the human. We can forecast the output given these constraints, but we can also change the output and then refine the constraints in the backward step. So let's look at this in a little bit more detail. As I mentioned, on one hand, we have these model hooks. They're just represented by color. They do correspond to different parts of the table. So for example, in this purple constraint here, if you look at the bottom, corresponds to eat type, name, price range, and customer rating. And then in the output side corresponds to restaurant, coffee shop, and pub, just to see a couple of the examples that would correspond to that particular constraint. So let's say we have a table input here. The Phoenix is the name of the establishment. The eat type is pub, and the food is French. And let's say the user would like to generate an output that just summarizes that part of the table. As a first step, the user will have the model just freeform generate the output. And the output from the model is the Phoenix is a French pub near Café Sicilia in the city center. So the model naturally used all of the table entry in order to generate this output. So we want to correct that. So in our interface, the user can actually add a correction that will take this longer output and shorten it. And we can do this by telling the model that, exactly what we want the output to be. So we give it an exemplar. So in this case, the Phoenix is a French pop. And that model output is then added to the actual output that has been generated by the model for all the other establishments. So that model output will generate an internal constraint in the model, which will then be used to generate all of these other outputs that you're seeing here. So for example, similarly, the Phoenix is a city restaurant, the Mill is a cafe restaurant, the Mill is an English pub, etc. Now, we might notice further down in that list that the model made a mistake. In this case, the name Strada appears twice in the output. So it's Strada is a all pub, and the word all actually doesn't make sense. So again, the user can correct this output, in this case by removing the word Strada and the word all, and then use that to generate more constraint, which then generate the output. So if you look on the top, you see the current constraints that are applied to these outputs, and you see that the one on the bottom here, Strada is a pub, is different from the rest of the constraints, which were actually what we had generated before. So this additional constraint doesn't change the predictions of the model for the previous outputs. It just applies to this particular output. Now let's take a step back and let's look at the model maybe at a higher level. So we have this inference network, and we have these outputs here called Y. And the user can actually basically generate the desired text output. And then from those desired text outputs, Y, we infer the control states, Z in this case, which again we call model hooks. So if you look on the lower right at the picture that I've shown you before about human AI collaboration, this basically corresponds to the arrows on the right, where we have an output that the user can change, and then the model infers the hooks that this particular output would need in order to generate similar output for similar input. So it's a constraint generation. The model actually uses these constraints, in this case in the beam tree search, in order to generate a particular output. So it will, for example, down this beam tree will not go certain paths because of the constraints that the user has applied. And if you will, that's corresponding to the arrow here on the left, where the user can actually modify the hooks directly and also then generate different outputs. Now, in order to make this easier to understand for the user, which by the way is still an expert in machine learning, but the user can look at this constraint graph. And in this case, as I mentioned before, we've added 2 constraints. And we even express this as a regular expression as shown here on the upper left. So the user can either edit this constraint graph directly using a graphical editor, or they can change the regular expression in text on the upper left. Okay, so what lessons did we learn in this project? This higher order constraint graph idea combined with direct user inputs is very intuitive for the users. And I think this is a lesson that should apply also to other deep learning models in other domains, for example, in computer vision. So instead of, for example, directly manipulating pixels, it is better to think about in terms of manipulations of a higher order constraint that will then influence the model output generation. However, this project also brought up a really interesting and I think deep question, which is how do we evaluate human AI collaboration? Which parts do we measure in terms of the automated text generation versus the human generation of the text? And could we evaluate models using both automated and human metrics? And that's, I think, a really interesting question. There are some interesting new benchmarks, for example, the GEM benchmark, that try to get at exactly this issue. But I think that's just a very first step. In addition to benchmarks, we actually need tools and better metrics, I believe, that will make this type of human AI collaboration much easier to evaluate moving forward. So Genie is also going to be released open source, and there's going to be an online demo. It's not quite online yet. Again, the paper will appear this October at IEEE Viz, at which point we'll release the demo at this URL here shown on the top. And as you can see again in this interface, there is a lot more to it, and including, for example, the beam tree shown here on the lower left that I didn't have time to talk about. So let me get back to my call for action that I mentioned at the beginning of this presentation. Again, I have 3 messages. I do think interfaces to deep learning systems need to follow these principles of human-centered design. And what we learned is that there is no substitute of working with experts in machine learning in collaboration with experts in visualization and HCI. And we're fortunate that our team has both of them. So we're going from what shown here in the middle on the top was, the model design informs the visual interaction design, to the picture on the bottom here in the middle, that there is also this loop backwards, that the visual and interaction design then informs the model design. And I think it is really crucial to have experts on both sides of this balance. The second message is that to reestablish the human agency over deep learning systems, we really need to have interactive collaboration with these systems. And I like, to think of it similar to this picture here, where, this user here is manipulating the robot in order to teach it a new way of manipulating an object. And this is really a collaboration. The robot wouldn't know what to do without the human operator. Similarly, I think we need to be able to influence these deep neural network models by directly manipulating them in a human understandable interface that is easy for the humans to grasp, but that have a direct influence on the model's output. Which brings me to the third message, which is that, in our opinion, neural network models need to be extended to include these intermediate representations or hooks, so that they can be understood and acted upon by humans. So it's a little bit like this cartoon picture here where it says which line would you pull in to catch the fish, and just by looking at it you don't really know. However, if you have the right hooks and the right lines, in this case these latent variable hooks, it is actually very obvious how you can manipulate, in this case the fish, but in our case the deep neural network model. So I would like to thank you for your attention, and I'd like to acknowledge our sponsors, NSF, and again point you to all of the source code, all of our papers, and also interactive demos that are online or that soon will be online. Thank you.